Welcome to Module 13, Motors, Drives and Power Quality. In this module, we connect the BAS command to what actually happens in the field. A controller can request motion, but the motor, the drive, the electrical supply and the mechanical load determine the real result. By the end of this module, you should be able to look at a fan, pump, tower or compressor and ask better questions before changing logic or replacing parts. Here are the learning objectives for this module. We are not trying to make every BAS professional an electrical engineer. The goal is practical field understanding. You need to know how motors behave, how VFDs receive commands, how frequency relates to speed, and how to interpret current, power, speed, mode, and fault data. Most importantly, you will learn to separate what the BAS requested from what the drive, motor, and process actually did. The primary outcome is simple but very important. Command, drive state, motor output, and process response are different facts. BAS command of 50% does not prove the drive is accepting that command. It does not prove the motor is producing the expected speed. It does not prove the pump is creating the required differential pressure, or the fan is moving the right air. In the field, we verify each step before we blame the controller. Most large building systems depend on motors. Fans, pumps, compressors, and cooling towers convert electrical energy into mechanical work. The BAS may enable the equipment, command a speed, or reset a set point. But power switching, overload protection, short-circuit protection, and phase protection are handled by dedicated electrical devices. The BAS monitors and coordinates. It should not replace required electrical protection. A three-phase induction motor works because the stator creates a rotating magnetic field. Synchronous speed depends on frequency and the number of motor poles. For example, a 4-pole motor on 60 Hz power has a synchronous speed of 1800 RPM. The actual rotor speed is slightly lower under load because of slip. When current is high, do not assume one cause. It could be overload, mechanical binding, low voltage, voltage imbalance, or another motor problem. Motor protection is a boundary that BAS professionals must respect. The BAS can monitor run status, fault status, and sometimes specific fault codes, but it should not replace overload relays, short-circuit protection, phase loss protection, ground fault protection, or required safety devices. In a real service call, always understand what the BAS is allowed to do and what must remain under approved electrical protection. A variable frequency drive typically includes a rectifier, a DC bus, and an inverter. The rectifier converts incoming AC to DC. The DC bus stores and filters energy. The inverter then creates variable frequency, variable voltage output to the motor. The drive may accept commands from a keypad, analog signal, digital inputs, network communications, or internal PID control. Command source clarity is critical. A drive in local mode can ignore the BAS while still showing values on the network. When the BAS command and drive output disagree, do not start by replacing the BAS controller. First check the active command source. Is the drive in local mode or remote mode? Is it following the keypad, an analog input, BACnet, Modbus, digital inputs, or an internal PID loop? Also check bypass status, minimum and maximum scaling, handoff auto status, and network priority. The controller may be doing exactly what it was told to do, while the drive is listening to something else. Frequency influences speed, but it is not the entire story. For an induction motor, speed roughly follows frequency after accounting for slip. A fan motor at 45 Hz may run near 75% speed. For centrifugal fans and pumps, the affinity laws help estimate flow, pressure, and power. But constant torque loads do not follow the same cube-power relationship. Always connect the electrical output to the mechanical load and the process result. Lower speed can save energy, but minimum speed is not just a software preference. It may be limited by motor cooling, bearing lubrication, fan or pump stability, minimum airflow, minimum water flow, resonant frequencies, process requirements, or the drive control range. Before lowering minimum speed, confirm the approved equipment limits and validate the process outcome. Saving energy is not success if the equipment becomes unstable or unreliable. Acceleration, deceleration, and restart behavior affect the mechanical system. A pump ramped too quickly can create pressure stress or nuisance trips. A fast stop can contribute to overvoltage or water hammer. A ramp that is too slow may fail a process requirement or delay ventilation. Restart behavior after power loss also matters. Automatic restart may be acceptable for some systems and unsafe for others. Define it intentionally and test it with the system. Bypass can keep equipment running when a drive has failed or is being serviced, but bypass is not the same as normal variable speed operation. In bypass, the motor usually runs at line frequency, often full speed. The system may satisfy airflow or flow, but it may lose pressure control and waste energy. The BAS should clearly monitor drive mode, bypass mode, commanded speed, actual speed, fault code, motor current, and run status. Power quality is where BAS, electrical design, and equipment reliability meet. VFDs can contribute harmonics, long motor leads can create voltage stress at the motor terminals. Grounding and shielding problems can create communication issues, unstable signals, or equipment damage. BAS managers do not need to perform advanced power quality studies, but they must recognize symptoms, capture evidence, and involve qualified electrical support when needed. Motor current is useful, but it is not always a direct measurement of load. Current can be influenced by voltage, imbalance, power factor, efficiency, operating mode, and mechanical condition. When performance or savings matter, measured power is stronger evidence. Good troubleshooting trends command, frequency, current, power, drive mode, fault data, and process response together. One number rarely tells the whole story. These worked examples show how simple calculations support field judgment. First, synchronous speed. A 6-pole motor at 60 Hz has a synchronous speed of 1200 RPM. Actual speed will be slightly lower under load. Second, fan power. If a fan uses 40 kilowatts at full speed, a 70% speed estimate gives about 13.7 kilowatts using the cube relationship. But remember, that is an estimate. Verify with measured kW when possible. Here is a realistic field scenario. A pump begins tripping on overcurrent after a controls upgrade. The easy reaction is to blame the pump or raise the trip limit, but the trend shows the pump ramping quickly while downstream valves are still closed. The pump reaches high head and low flow. The better correction is sequencing. Open the required flow path first, apply an approved acceleration time, then validate current, pressure, flow, and stability. These are common mistakes in motor and drive troubleshooting. Do not assume VFD frequency equals exact shaft speed. Do not apply fan and pump affinity laws to every type of load. Do not ignore motor cooling at low speed. Do not miss bypass mode. Do not use current as the only load indicator. Do not allow automatic restart without reviewing risk. And do not ignore harmonics, long leads, or grounding concerns. Each mistake comes from treating one fact as the whole story. Use this checklist before changing logic, ramp times, minimum speeds, or drive parameters. Confirm motor nameplate data, driven equipment data, command source, local or remote mode, approved minimum and maximum speeds, ramp times, bypass status, fault history, current power, and process response. A strong review protects equipment and makes the next technician's work easier. Let's apply the module principle. The BAS command is 50%, but the drive output is 60 Hz and the fan runs at full speed. The best first action is not to replace the BAS controller. The best first action is to check local or remote mode, command source, bypass status, scaling, network priority, and internal PID mode. You are tracing the active command path before making a hardware decision. To complete this module, build a motor and drive evidence package. Select one fan, pump, tower, or compressor. Record the motor nameplate information and the drive data visible to the BAS. Capture command, actual frequency, current, power, mode, bypass status, fault codes, and the process response. Then identify one risk, one missing point, and one improvement to the sequence or monitoring. In the next module, we move from motor output to measurement confidence, sensors and measurement systems.